Okay. So we'll discuss the axial magnetic field produced by a current in a circular loop. Axial magnetic field produced by current in a circular loop. Axial magnetic field produced by a current in a circular loop. So what is circular current in a circle? We have discussed about straight conductor, right?
Huh.
So here what we'll do, we'll take a circular loop. Let's say this is a circular loop.
Mm-hmm.
And current is equal to this.
Okay.
Find out, let's say this is the axis. So at a point on the axis, let's say P point on the axis, we'll find out what is the magnetic field. We'll find out what is the magnetic field. So here, axis. So here, we'll take a small length element, dl, and due to this dl, small length element dl, what will be the magnetic field here? We can use Biot-Savart's law.
Huh.
The
Right. So what?
current L is this direction, right? L is this direction,
Yes.
and this is your R,
Mm-hmm.
and let's say this is your Z, distance Z from the axis. Now, what will be the direction of magnetic field? Magnetic field is perpendicular to R. That means this is the magnetic field direction, let's say.
Huh.
This is your dB.
Yes.
So magnitude of dB as per Biot-Savart's law is
Omega. Sorry. Mu not. Uh, I dl sin theta by 4 pi r.
mu naught by 4 pi r sin theta by r square. Here at E point, the this whole Circle,
Integration.
complete circle. So what I'll get?
So we
I'll
need to
integrate it. I'll
integrate.
integrate it.
Yes, integration of the whole part.
So this will be
We did that integration, no, sir, in
we did the
amps.
integration for straight wire. Now we'll do for
Uh-huh.
this loop.
No. Yes. So limits will change.
So limits for this will be for straight wire. So here what we'll do, mu naught by root 1 and constant by outside.
And they outside. DL sin theta as per.
The angle between DL and R, this angle na
Oh,
always 90.
okay.
Sin 90, it will be sin 90,
One
so it will be 1. So integration DL by
by
R
R
square.
square. So R square and did go
And
outside like I.
it will be integration of dB cos theta. Why dB cos theta? Now see, this angle will be theta.
Huh.
Okay, this angle will be theta. And which angle is theta? This angle, this is radius. This angle is theta. Theta is
Okay.
the angle between the radius and let's say this r vector, r distance from this length to the point P.
Mm-hmm.
So if this is theta, this is 90. This is 90 minus theta.
Minus theta.
And this will be again theta, not theta.
Minus theta
This is
plus
theta,
theta.
this is 90, this is 90 minus theta. This is 90.
90 degree. Huh?
Draw a perpendicular here.
Yes.
So if this is theta, 90 minus theta, this one will be theta. Okay. And if this is theta, and we can prove this dB is perpendicular to r. So if this is theta, this will be 90 minus theta.
90 minus theta.
And again, this is parallel to this base. So this
Yeah.
and this is 90 minus theta. This is 90 to this. This one is 90. So 90 minus
Huh.
theta. So this one will be
Theta.
so we can prove that this is theta. Component of this will be theta. Vertical direction will be dB cos theta.
dv cos theta. Huh?
So whenever finding the total field,
Okay.
we take dB cos theta.
dv cos theta.
So dB cos theta for this one, dB cos theta for this one, dB cos theta for this one, all the dB cos theta we have to integrate.
Yes.
What about the dB sin theta component? Because dB will have another component also, dB sin theta, this one.
Mm.
So we might think
That
that what
is.
about this dB sin theta? What happened to
Uh,
it? Why you are not including here in the calculation of total magnetic field? Because you see that suppose this is a circle. So for each
mhm.
element there is a diametrically opposite element available.
Yes.
For this element there is a diametrically opposite element available.
Huh.
So what we can do is If this is dB sin theta for this length, it will be opposite direction.
dB sin theta.
Suppose for this length dB sin theta will be here, backside for backside component it will be to the opposite direction.
Other
So
side.
all the dB sin theta, for each dB sin theta at for a length, there will be diametrically opposite dB sin theta which is opposite direction, which will cancel it. So all dB sin
अच्छा
theta will cancel out to 0. So dB sin theta will have no contribution. dB sin theta will
no
cancel out
contribution.
by the vertically opposite, diametrically opposite your lengths will be cancelled out. Will be cancelled out. dB sin theta will be cancelled
Cancelled
out.
out.
Good. Now dB cos theta, dB cos theta integration is b. So and there is another cos theta also. Now what is the cos theta here in this triangle? Cos theta
Which
is
one?
base by hypotenuse.
Uh,
Take radius and
by
hypotenuse
R.
is r. So you can write that cos theta is r by r, which we can write r by smaller is z square plus r square root over.
Root of z square plus r square half.
Now we can replace it. And what is the integration of dl? If we integrate dl, we'll get all the circumference of the circle, right? So that is 2
Yes.
pi r. So if we
2
will
pi
write
r.
mu naught by 4 pi I cos theta is r by z square plus r square root over dl is 2 pi r
2 pi r.
and r square is z
Z
square
square
plus
plus
r square. So what we are getting? We are getting that total magnetic field by this is mu naught by 4 pi
2
I r
pi r
mu naught by 4
r
pi
square
mu
cos
naught
of
by
2 pi
4
r.
pi I
I
r
r
pi
2
r
pi r. 3 3 to the 3 by 2, sorry.
this magnetic field we are getting in z direction. So in your book it's written bz. We can also write the direction is bz. So we can
Okay.
write
1 by 2.
so we are getting mu naught by 2
2 I r square. Z
z square plus r square
r square.
3 by 2.
3.
This is the expression given in the book.
Okay. So Z is the axis, no?
Yes, that is the direction here we are taking. It can be if the ring orientation is changing, let's say this way, it can be x direction also. X, it can
अच्छा,
be
हाँ
bx
हाँ
also. Right? So you are holding the ring like that.
हाँ हाँ.
So different side. how our loop is oriented, right?
Okay. Now
It depends how our loop is oriented.
oriented.
Now there is the question sometimes comes. What will be the magnetic field at the center of the loop? Here it is on the axis, some point P we are finding out. At the center, what will happen? This
Okay.
Z value will become 0 because this distance is Z, right?
Distance is
So
very
at the center, what
so
will
r
happen?
square r square. Uh,
Value will become 0,
so it
right?
will be
So
how
at center, let's say, magnetic field at center, magnetic field at the center of the loop. What will the magnetic field at the center of loop? Putting Z equal to 0. Put Z equal to 0. So mu naught
by
I
2
r square divided by 2
2 r square
Z
to the
r
power
to the
3
power
by
r
2
square to the power 3 by 2.
by 2
So 2
to
2
cancel.
cancel. So r cube upon r square. So r cube cancel.
Yes,
So
and the
basically we are getting
r
mu naught I by 2r.
2 r.
This formula is important.
That 2r will become the diameter only, right?
2r, yeah. 2r is the 2 times of r radius of this loop. So 2
Yes.
times of r.
Small r.
Right?
Yes, sir.
Now, so this is a loop for one turn.
Mm-hmm.
This is a loop for one turn.
1 2.
If the loop will be having if the loop will be having, let's say, n number of turns,
Into n.
suppose n number of turns, what is the magnetic field at the center?
Uh, n
Multiply n.
into.
So for n turns, this will be used in many numericals. For n turns, mu naught n number turns by
So only at center, not at
yeah.
axis or
And on the axis also, you will multiply with this
anything.
right?
Just multiplying with an
For one turn, we got this expression. For n turns, n will be multiplied.
n. Okay.
So what we will do? Not one question. X and Y. Find the magnitude. Center of the center two coils. Y intercept. Equally equal current. A equal current. If the coil X has 200 tons and 20 centimeter radius, coil Y has 100 tons magnitude of X and Y. Here, Bx and By are the magnetic field at the center of the coils. So there are two coils. One is radius 20 centimeter. Both are 20 centimeter radius. Okay. One is having 200 tons, another is having 400 tons. So one is having number of ton 200, another is having 400. Current is also same flowing. So very easy. Just ratio we have to what will do.
And they said at the center, no? So we have to use uh, mu not I by 2r. Mm, yes, and mu not
Same current,
I by
same radius.
2. No,
So ये cancelled out, cancelled out, cancelled out, cancelled out. So Nx by Ny simply na.
yes,
And Nx is 200 tons.
100
And Ny
by
is
100.
400.
1 is 1 is to 2. Yes, yes. 1 is to 2.
Now discuss that is given in the next page magnetic field lines for a current loop and magnetic field lines for a current loop, then
Ampere.
magnetic field lines number of turns B equal to mu naught Ni by 2r, it is written,
Yes.
right? Okay. This analogy will draw it later. Now we'll come to Ampere's law, which I have already introduced you. What is Ampere's law? Ampere's law has an analogy. Law has an analogy with Gauss law of electrostatics, right? So Gauss law in electrostatics tells us what? That inside a closed loop, if the number of
Close.
charges are there,
Right?
flux linked with the surface phi equal to q inside by epsilon. This is what Gauss law of electrostatics tells us.
Yes.
Now Ampere's law tells us that if the current lies inside a loop, so the line integral, that is dl b, the magnetic field produced, let's say B magnetic field will be produced due to the all current which is inside together, that is I inside, let's say, is the line integral of all the, here also be all the line integral of this magnetic field. So basically B dot dl will do integration over this
It
closed
is
loop
U, oh
I
sorry,
inside.
U mu not by I in plus.
After all, the SI unit of current is named, right? The ampere is
Oh,
known as the SI unit.
yes, ampere.
Let us suppose calculate that what will be the magnetic field due to suppose a loop is given. Let's say this is the, these are the dot, this is the dot, this is the cross. Let's say cross means the current is going inside. Let's say dot means the current is coming outside. I2, this is I1 also. So net current inside this loop is and I4, and this is your magnetic field B. This is your dl. So the question is what will be the magnetic field, or what is the Ampere's law if we'll use, what will be the,
Only current that is going inside is I3, no?
yes, and I4 is
Okay.
the current which is going inside also, but it is outside the loop, so we have no rule it here.
Uh-huh.
Okay, so your
So,
BDL here is not
what?
I1 plus I2 minus I3, the net current.
Wait a
Two
minute.
current are this direction and one current is opposite direction. So the opposite direction current will create a opposite magnetic field which will reduce the field actually, right? The net field will be affected by the
Yes.
opposite current.
Okay. Ready. Oh,
So we can also write dot product is there, so we can write BDL cos theta
theta plus this minus this.
how we'll use the Ampere's law.
Then sir R I4 का क्या काम है?
Gauss law is also like that. Suppose this is a loop, inside some
Uh-huh.
charges are there and outside some charges are there. So flux linked with the closed loop, when we are finding out, we will sum these charges, not these outside charges. They're
Outside
just
okay.
given. There are some charges are there outside, but we are not including them in the calculation of the flux linked with the surface. Here also, we are not including
Same.
them the magnetic field with this loop.
Uh-huh. Good.
So now let us do one question using Ampere's law, and I have told you this one. that clear to है calculated
How
at a distance
that
r.
is
This law it will also come up the same mu naught I by 2 pi r.
yes.
That b dot dl integration equal to mu naught I, and
I
b dot dl is basically
B DL cos theta.
direction
Huh. One.
circle, so it is 2 pi r
2 pi r.
naught I or
B equal
dl,
to
that will be mu
mu
naught I by.
r by 2 pi r.
So now let us solve one question.
Mm-hmm.
Find the magnetic field due to a thick circular conductor outside and inside the conductor, the magnetic field. Let's say this is a conductor,
Mm-hmm.
and in this conductor we'll find out the magnetic field at a point P, which is
Outside.
at a distance, let's say small r, and radius of this conductor is, let's say, a. We'll
Mm-hmm.
find that magnetic field outside and magnetic field inside the point P. Let's say
Mm-hmm.
small r is here, r is less than a, and r is greater than a. So in two places we'll find out what is the magnetic field, right?
And
So how
inside.
will you calculate magnetic field outside? Is very easy, right? Just we calculated it is,
Huh.
it's a perpendicular distance, so magnetic field greater than a,
Mu.
that is,
Mu.
if we draw a loop here, so whole current I is there inside the loop, right?
Yes.
So let's case one, r greater than a. So for that we will use the Ampere's law. So b dl integration is mu naught I.
And
B dl integration is mu
mu
naught I.
not I.
The b dl integration for a closed loop is b into 2 pi r
Where?
naught I, or
Yes.
say b equal to mu naught
2
I
pi r.
by 2 pi r. That means the is inversely proportional to radius r. That means
Yes.
if you draw a graph, come to the graph, when distance from the conductor will increase, magnetic field will decrease.
Decrease half.
What about the current for a loop or a position point which is inside the conductor?
Back.
What will be the magnetic field that is inside the conductor?
Same formula, but
What is the magnetic field inside the conductor. So magnetic field inside the conductor, when then the loop will be small, and in
हाँ
this loop a fraction of current is passing, not the whole current.
अच्छा हाँ
Because if a loop is outside, the whole total I is flowing.
yes
But if the loop is, if we are considering a point P inside, then we are considering a loop which will have a smaller radius r, let's say, but this loop will not contain all the current I. A fraction of current, let's say I dash, it
yes
is containing. So how will you find that I dash? Now let's say this complete area of cross section of this conductor is pi r square. Just
yes
go for
yes
the hmm. So for pi r square area, the current is I, because I is distributed all over the pi r square, right? Full. Getting? I is distributed all over the area.
yes
So for unit area, if we use unitary method, how much current will be there? I by pi r square.
yes multiplication yes
Oh, radius we have taken a, pi a square. I by pi a square.
yes
Now for a small radius r, then the inside conductor, this one is the inside conductor that we have taken radius r smaller, right?
हाँ
So for that area, what will be the pi r square? So for pi r square
yes
area, what will be current? I by
uh,
pi
I
a
five
square multiplied
I
by pi r
is
square.
yes 5 by 10 is square हाँ you not
Mu
I
naught
R
I
square
dash
by square
or mu naught I r square by a square, or B dl is here again B into 2 pi r equal to
by
mu naught I r square by a square.
R square is square
R square cancelled out.
R
So
R
B
cancel
you are getting mu naught I
2
by 2 pi a square
2 pi is
r,
into a half
and
yes
this is what? This is you are getting B is proportional to R. That means magnetic field, when it is increasing
inside the
up to the radius A, it is increasing.
huh and outside it is decreasing
Outside, as the R will increase, it will decrease,
yes
right? As the R will
okay
increase, it will decrease, and as the R will increase up to radius A, it will basically,
it will decrease
it will
in
it will increase. So if we'll draw a graph, sometimes comes.
okay
If we'll draw a graph between, if we draw a graph inside and outside. So how the graph will look like?
Inside it will be straight,
Increasing up to radius A.
increasing.
We draw a graph like this,
B R.
and graph will draw B versus R.
Yes,
So from
straight line.
0 radius it is 0 approx up to A it is increasing,
Increasing.
and
Yes,
straight line directly proportion,
direct. Yes.
right?
Huh. Yes.
B R. So B proportional to R, it's a direct proportion.
Mhm.
So for direct proportion it will be a straight
B.
line up to A.
It will be increasing. Huh.
Now after this radius A, R will decrease 1 upon R. 1 upon R graph is like this,
Huh.
right? Decrease like this. So this is B proportional to 1 upon R.
One upon R.
This is the graph. Inside a conductor and outside the conductor, the magnetic field due to the conductor inside and outside.
Inside it will be increasing. Outside it will be decreasing. You know? Yes.
Now we'll discuss solenoid. Application of Kirchhoff's law in solenoid. Magnetic field of a solenoid and a toroid.
Oh, Taurus. Okay.
What is solenoid? Magnetic field of a.
Solenoid.
So what is a solenoid?
And
What is a solenoid?
solenoid.
Solenoid is basically it's a helical type coil, right? It's a helical type coil.
Mm-hmm.
Basically, we consider the radius of the coil must be less than length of the coil. Then we'll keep it in the category of the solenoid. But
Achha.
R of the R must be less than L. Then
Yes,
we'll
yes.
call it solenoid.
Okay.
Else we'll call it loop. So sometimes the students
Mm-hmm.
confuse the loop equation and the solenoid equation in the numerical special. The solenoid, and suppose if it is having 100 turns but one turn over the other turn, ऐसे ऐसे ओवरलैप हो गया टर्न, एक के ऊपर एक, एक के ऊपर एक,
Okay.
let's say 100 turns.
Coil.
This is a loop of 100 turns. This is not a solenoid.
L is not. Yes.
Loop of 100 turns. So loop of 100 turns means you will use the formula, the magnetic field at the center of the loop B equal to
Mm-hmm.
that we have just written N mu naught I
No,
by
not
2R.
I. R. Yes.
Now we'll
Yes.
just derive this equation for solenoid. If the equation is given that for a 100 turns solenoid or which R is less than L, right? 100 turns. This is also 100 turns. But
Okay.
these 100 turns are spreaded,
R
not
is
one
less
over another.
than.
Then we'll
Okay.
call it solenoid and we'll use the formula for the solenoid. At the center of the solenoid, what is the magnetic field? Let's say the question come. So whether you will use
Okay.
solenoid formula or loop formula depends upon if it is mentioned solenoid or if radius and length of the solenoid is given and radius must be quite less than the length.
Thunder
Or
left.
it is mentioned that if it is not overlapped over one and another. Like these 100
Okay.
terms are spreaded. Then only we'll put it in the category of the solenoid. The solenoid 100 turns, the formula will derive that magnetic field inside the solenoid is B equal to mu naught N by Li. Or we write B equal to mu naught small n I. Small n is number of turn per unit length.
Okay.
This is the magnetic field that will be inside the solenoid.
Solenoid.
Magnetic field inside the solenoid.
Solenoid.
We'll use ampere loop and we'll prove it.
अच्छा that big deal is good one.
We'll do that. And what is toroid? What is toroid? Toroid is basically toroid also same formula will get B equal to mu naught Ni small ni. Small n is what? Capital N by L. Capital is N is the number of turn. So number of
Number of
turn per
turns.
unit length. N by L is small n, right? N by L is
Yes.
L is small n, and this is
Small
what?
one.
What is toroid? Now if we bend the solenoid in circular form, इसको ऐसे बेंड करके सर्कल बना दें सोलेनॉइड को, तो उसको हम लोग बोलेंगे टोरॉइड. इधर करंट
Okay.
मिलेगा सप्लाई.
हाँ.
सोलेनॉइड को बेंड करके गोल बना दे, सर्कल टाइप
तो
का बना दे, तो
toroid.
उसको बोलेंगे क्या?
Toroid.
Toroid also when the current will flow, there will be magnetic field. It's also a multiple loop, right?
हाँ.
Multiple loops are there.
Yes.
So inside, due to each loop, there will be magnetic field inside, right?
Yes.
And due to this loop, this magnetic field they will add up and we'll get the magnetic field at the center of the loop. So here also toroid also will be getting that B equal to mu naught N by Li. B equal to,
Same only.
yeah, same will be getting, or
You
will be
know,
getting
small and bad.
N, will be getting the same. This is inside. This is magnetic field inside.
Instant. Okay.
Outside, magnetic field strength is spreaded out, so strength is very less, approx 0.
हाँ.
Both solenoid and
For
toroid.
solenoid.
Magnetic field outside will be very small. Okay.
Yes. And for toroid.
Toroid also, magnetic field will be very small, approx 0 outside the toroid.
Okay.
So we'll derive it in the next class,
Mm-hmm.
and I think this is the last part, and some two
That
three
is
concept
okay.
we'll skip.
Yes.
We'll discuss it also.
हाँ. Yes.
Okay. So let us
Yes.
stop. Okay.
Okay. Bye.